you. Good morning, everybody. Yeah, so I have talked about this before. It's basically an updated version of my talk from 3 years ago, here almost at the same place. So I didn't really know what to talk about. So the title is Lessons Learned, but it's like an overview of some results we have obtained and some lessons learned and some opinions for the upcoming discussions. So we have done a long-track interferometry for current measurements from space since 2000 here with the SRTM that was already mentioned by Bertrand. So for those who are not familiar with SAR interferometry, so we had the main radar antenna here in the cargo bay of the space shuttle, and there was this boom here with another antenna, and the main purpose here of the second antenna was to do cross-track interferometry, so it was far away from the main antenna in the direction perpendicular to the flight direction. But what matters to us is this little distance here in flight direction, which was 7 meters in this case, giving us about a half millisecond time lag between the two images, and that's what you can use for the Doppler measurement to derive the currents. So we did that for the first time with this instrument here, which was far from optimal, but it was the first opportunity. Then later in 2007 we got TerraSAR-X, which was similarly suboptimal. It had only one antenna, but could be divided into two parts, like shown here, to do interferometry with an even shorter long-track baseline. Then in 2010 we got a second TerraSAR-X flying in close formation with the first one, TanDEM-X. This allows us to do interferometry with more optimal baselines. I will show some examples from that. And here is the famous first result that I obtained. Yeah, I almost forgot about this other one here of the French coast that was promoted very much by Pierre Flamand, I think. This is the first paper, I think, that we published together. Pierre was a co-author on this one. So this is my current field here for the Dutch Wartensee, obtained from the space shuttle data, showing only the line of sight component here. So the shuttle was flying this way, looking to the right. And this was a corresponding model result here from colleagues in the Netherlands, showing very similar patterns. You can see that the main reason why the current pattern is like this is from the bathymetry here. We learned from this that if you have a poor absolute phase calibration, which was the case here with the combined cross-track and long-track interferometry, you can tune the phases such that here along perpendicular coastlines perpendicular to your look direction, where you know there should be no current, you turn it to 0, and then almost everything else will fit. You don't need to apply a lot more corrections for the wave motion. So this was a result obtained in that very simple way, and we found that we obtained an accuracy of about 0.1 meter per second at an effective spatial resolution of 1 kilometer, which was consistent with our theoretical expectations. It's a little low spatial resolution, but given this very suboptimal setup of the space shuttle, that was exactly what we expected to get. And here's another example for the Elbe River. Here the velocity component in the look direction again. And because you know that the flow must somehow follow the shape of the river, you can use this component that you measure to derive the full current, which looks a little noisier here. Then we had again a model result that looked like this. Of course not so noisy, and the line of sight component from the model looks very much like our line of sight velocity. So the lesson learned here was that when you have a river, you can almost get a complete current vector here following the river. Then we had a bunch of TerraSAR-X results. The first ones are here from as early as summer 2008. The Elbe River mouth here under 6 different tidal phase conditions. So here you have a strong flow to the right, and then here at the end you have a strong flow To the left, again, we had model results for the same tidal phases, and you can see pretty good agreement. We published this a few years ago. So here the time lag was only 0.11 millisecond. That's a factor of 30 or so shorter than it should ideally be. And still we got a relatively okay data product here for these first tests. Here's another example from TerraSAR-X with these internal waves here at Dongsha. Here you see the conventional SAR intensity signatures. This is Dongsha Island. Here the whole thing is about 30 kilometers wide. So these are pretty large internal waves. This is what the original phase image looks like, and if you process it properly and superimpose the velocities over the intensity image, here you get combined velocities and intensities, and we showed that when you have the intensity modulation and velocity modulation together, you can derive the internal wave parameters with more certainty and more accuracy than if you just have the conventional intensity images. And we took a lot more long-track INSAR images for a bunch of experiments. I will not talk too much about that. Here is something else. This is for Pentland Firth, the Orkney Islands, in a comparison between divided antenna mode data from the single TerraSAR-X satellite, which is shown here at the top, intensity, coherence, and the original phase image. And at the bottom there will be a TanDEM-X result with a better baseline. This looks pretty bad as a phase image, but if you do some smoothing and you convert it into Doppler velocity, you can get something like this here at an effective resolution, again on the order of 1 kilometer. Compared to that, from TanDEM-X with a much better long-track baseline, here with a time lag of 3.3 milliseconds instead of 0.15, you get this right from the beginning here. This, you remember, this here was obtained after smoothing. The comparable product looked like this, very noisy, so I had to do the smoothing. Here I get at the original grid resolution here that I use of 25 meters squared, I already get a pretty clean current field, so I get a much better data quality with a better baseline. Interestingly, the coherence here is already going down a little bit because signal is beginning to decorrelate, but I have a much better sensitivity to the velocities, which outweighs the problem of the reduced coherence. Then we also looked a little more at the resolution here. This is again an intensity image now shown on the grid of 8.4 meters squared, so this is higher resolution. Even at this resolution you can see the wave motions. Here you can resolve the orbital motions. And so we did an analysis here when you start with the full resolution phase image here from the dual receive antenna mode and from TanDEM-X. This looks much noisier at full resolution than that, and now you can smooth it more and more. You average over 2x2 and 4x4 and 8x8 pixels, and eventually on both sides you will get a relatively smooth looking current field. Here the noise goes down, but at the cost of reduced resolution. And if you plot all of that, you find here when you plot after averaging how many samples, where is your residual RMS variability, you find that here at the dual receive antenna mode you have to average over about 1 square kilometer to reduce the remaining noise here to 0.1 meter per second. With TanDEM-X with a better baseline here we could average over just 1,000 square meters, so that's a factor of 1,000 better. So with an effective spatial resolution of 33 meters in this case, we could reduce the noise to 0.1 meter per second. Here are a few more examples from TanDEM-X just to show that we have them. Here you have an effective baseline of 12.3 meters, so time lag of 1.6 milliseconds. Coherence looks like this at that baseline. Phase image looks like that. Converted into velocities, it looks like that. So again, you don't need to do much smoothing there. You already get a pretty good velocity picture. If you do some smoothing, it gets even better in some areas. The next example here has a baseline of 34 meters. So that's now the American West Coast, 4.5 milliseconds here, intensity image. Coherence image looks like this. Coherence is going down now because the time lag is increasing, but the phase image looks like this, quite nice, still converted into Doppler velocities, looks like this. And now we have some noisy areas here where the intensity was low, the coherence is not so good, but you can, again, do some smoothing to even get some good results in those areas with relatively little smoothing compared to what you would have to do with divided antenna mode data. And there's another example here from the Strait of Gibraltar, now with a 50-meter baseline, 6.5 milliseconds time lag. Coherence looks pretty bad, but still we get a pretty good current field. We can still see wave motions. So there's quite a wide range of time lags here that give you relatively good data within a long track INSAR. And another thing we did here, just because it was possible, we acquired this series of images here while the satellite pair was moving from Antarctica northward here with an increasing distance between the satellites, and then again here on another path here we took another 10 images. So this was a series of consecutive images with the satellites moving apart from each other and the time lag increasing. Here, in this case, from 1.8 to 5.4 milliseconds, here from 3 to 6.9 milliseconds. We could use this to plot the measured coherence as a function of the time lag. I think this had never been done before, that the coherence was actually measured directly this way as a function of the time lag, instead of deriving it indirectly from Doppler bandwidth. And here are some model results in colors behind it with some explanations there. The main conclusion here is that the data fit quite well to our theoretical expectations. So we believe we understand relatively well how to model this kind of data product. And so if we have a good model, it also means we can make good predictions and good simulations of proposed future systems. Here are some lessons learned. Data quality is consistent with model predictions, so we understand how to predict this stuff. We obtain good results for a relatively wide range of time lags and incidence angles if we can use TanDEM-X. We have demonstrated that we can get a residual error of 0.1 meter per second at resolutions as high as 30 meters. Biggest problems that we have encountered here are, of course, the availability of TanDEM-X. It's usually not available for this kind of measurement because it was not optimized for that. Then the SAR look direction is not always what you want when you want to look into some rivers, or you want to look at features with a strong north-south current component. You cannot catch them very well with these satellites that are just looking sideways. Instrument noise can be an issue with TerraSAR-X, which has a pretty high instrument noise level, and the absolute phase calibration can be an issue. And with the divided antenna, there can also be an issue of ghost signatures due to azimuth ambiguities, but I think we have that under control, and it will not happen with more optimized systems where the antenna pattern and the PRF and the Doppler processing are optimized together. Now something totally different that I wanted to show you as something new here. This is a staring spotlight image from TerraSAR-X showing the California coast. This at full resolution would be 1.08 meters times 0.17 meter resolution, very high resolution, very small pixel size. The whole image is relatively small at this resolution. It's only 7.5 by 2.8 kilometers. That's the size of these staring spotlight mode images. This is acquired with an integration time of 6.72 seconds. And here over the ocean it leads to blurring. It's like taking a photo with a long exposure time. You cannot really take advantage of the high resolution if you just take the standard product here with its full SAR processing. But you can do some special processing here. You can first of all reduce the processing bandwidth. Look here at my bandwidth and how the image becomes sharper. It's like reducing the exposure time to reduce the blurring effect. And then you can say, okay, if a much narrower bandwidth here gives me a better image, I have all these data here, so what can I do with these data? The data from different parts of the Doppler spectrum correspond to different time steps during the SAR integration time. So you can, instead of doing different bandwidths here, you can just do one narrow bandwidth and scan this Doppler window here through your Doppler spectrum. And when you look what happens here, you see now the waves moving within. You can see how far they move within these few seconds that you can cover here with your integration time, which is much longer now than it would be with a conventional SAR, where the whole integration time is only a half second or so. You can really see with your naked eye that the waves are moving. If you zoom in a little bit, you can do this. There is again the wave pattern here in the original data, and if you filter this a little bit, which I have explained in some more detail in some other talks, but not in this one, you can get this filtered image here of the wave signatures. So now you can see how fast the waves are moving. You can do a frequency wave number spectrum, and you can compare it with the dispersion relation. So if you do this correctly, I'm still working on that, it's not finished, but it should be possible to derive water depths and current vectors in a similar way as people do it with marine radar data. So this is another way to measure currents. You look at the moving wave patterns and how they are Doppler shifted due to the current vector. Now, SEASTAR, this goes back now to a long track INSAR, and Christine will give a talk about this, where she will explain in much more detail. So this is a proposed future long track INSAR system, which in my opinion is what we should get. And as just for inspiration here for the coming discussions, I wanted to summarize what I think about it. So this will produce 1 kilometer resolution vector wind and current fields within the 170 kilometer swath, which is quite nice. It uses well-established long-track INSAR and wind scatterometry techniques. Is my time over? Yeah, it's almost finished. It's almost finished. This is the last slide. So there will be synergies with the proposed Doppler scatterometers. So when you understand how to use the Doppler scatterometer data, you will understand how to use this data. And it's a single satellite standalone system that does not depend on the availability of other satellites as illuminators or so. If this thing flies, it will work by itself. So those are all strengths that I see. The only weaknesses I see, one thing is there's a limited coverage in space and time that you always have with SARs. They can be on for only a few minutes per orbit. They cannot run permanently like a scatterometer. And they have a relatively narrow swath, in this case 170 kilometers. So you cannot get global coverage within one day or so. And another issue, in my opinion, is so far there is not enough support and demand from the potential user community. These are the biggest weaknesses of such an advanced long-track INSAR system. And my recommendation here, which we can discuss further when we come to the discussion, I think we should have Doppler scatterometers first that will pave the way for using this kind of data product, combined wind vectors and current vectors at a lower resolution than this, but more or less global and as a routine product. And when the user community has learned how to use this, we can advertise SEASTAR as the next thing to complement these data with higher resolution and better data quality where it's really needed, in coastal areas, in rivers, and so forth. And that's the end of the presentation.
Thank you, Roland. With Chair's prerogative, I take the first question.
Yes.
Spotlight mode looks really good. So can you... the spotlight mode looks really good. So can we have a spotlight mode at the same time that we do our SKIM for drift campaign in November? Can we have a chat with you? Because it would be very useful.
Well, yeah, spotlight mode can just be ordered.
So we need to
for
organize
our
that.
Satellite station, we can order that. So we can look up how it fits. It's only a small area, as you can see, that we can cover, but if it's the right area, it may be good enough. Yeah, so that would be nice to do that together, yes.
Okay. Questions then? Come on, must be one. Christine.
Thanks, Roland, for this impromptu review of the SEASTAR proposal, which I didn't expect. Really, just to pick up on the point about the lack of user support for this type of product is not just a problem for SEASTAR, it's a problem for all the SAR missions, with real difficulties breaking through to the scientific community about the importance of Doppler measurements of the ocean, which is precisely what this workshop is about.
Yeah.
So,
Yeah.
not just about SEASTAR.
Yes, but that's the only problem we need to solve with SEASTAR, while there may be more problems with some other missions.
Yeah, I mean, I think you have to take this back to applications. There are a number of applications that you can use the measurements for directly. But the real challenge is to actually start a parallel activity to help the modeling community develop the relevant forward operators which can use this data in anger. Because that is a stumbling block at the moment. You know, today, modeling community wants altimetry because that's what models have been developed on for 30 years. We need to change that. It's not to say we don't need the altimetry, we do. But we have additional information to put on top of that. Thank you, Roland.